Welcome back to the deep dive. I want to start today's session with a question that, on the surface, it sounds incredibly simple.
Okay.
It might even sound a little bit stupid, honestly, like something a toddler would ask you out of nowhere. But I promise you, by the time we are done with this hour, you are going to look at your kitchen sink, your garden hose, and definitely the next fire truck you see, just completely differently.
I love questions that sound simple but aren't. Those are usually the absolute best ones. Let's hear it.
Okay, the question is this. Is water actually wet?
The classic philosophical trap.
Right.
I mean, if water touches you, you get wet. But is the water itself wet?
Exactly. But I don't mean it in the linguistic sense or the philosophical sense. I mean functionally.
Mechanically.
Yes, mechanically. Because we grow up thinking of water as the ultimate liquid. It's the universal solvent, right? With the universal fire extinguisher.
You see a fire, you throw water on it, it's pure instinct.
Right. But here's the reality that industrial firefighters, wildland crews, and safety engineers deal with every single day. Sometimes water just isn't wet enough.
That is a scientifically accurate statement, as strange as it sounds to say out loud.
It fails, it beads up, it rolls off, it sits on top of a burning pile of mattresses or a bale of cotton or a peat moss fire and just...
Does nothing.
Yeah, it does nothing. It effectively bounces off the fuel. It's like the water is wearing a raincoat.
Right. And that is entirely because of surface tension. Water has a skin.
A skin.
Yeah, it's highly cohesive. And in the world of high-stakes fire safety, that skin is the enemy. I mean, if you can't break that skin, you basically can't put out the fire.
So today, we're looking at how we hack the physics of water. We're doing a full deep dive into NFPA 18. That is the standard on wetting agents.
Specifically looking at the 2021 edition.
Yes. This is basically the rule book for making water into superwater.
Superwater is a pretty fair way to put it, honestly. This standard, NFPA 18, is the rigorous scientific framework that defines what a wetting agent actually is.
Because it isn't just about dumping dish soap into a fire truck.
No, not at all. You can't just hope for the best. It's about complex chemistry, toxicity, corrosion, and most importantly, the ability to penetrate deep-seated fires that normal water simply cannot touch.
I have to say, going through this document for this deep dive, I was completely blown away by the level of detail.
It is incredibly dense.
We aren't just talking about, does it put out the fire? We are talking about rainbow trout survival rates.
Yep.
Rusting metal coupons, specific acid baths for cleaning those coupons, and literally heating steel rods to 1100 degrees Fahrenheit just to prove a point.
It covers the entire life cycle of the chemical. From the jug sitting on the shelf in the hot fire station, to the pump it flows through, to the fire it extinguishes, and finally to the environmental impact after the fire is actually out.
It's a massive holistic standard.
It has to be, because the stakes for the people using it are incredibly high.
So let's start with the absolute basics. For you listening who might think this is just heavy-duty soap, what exactly is a wetting agent, according to the NFPA?
If we look at Chapter 3, the definition is quite specific. A wetting agent is a concentrate that, when added to water, reduces the surface tension and increases its ability to penetrate and spread.
Penetrate and spread. Those seem to be the two magic words for this whole thing.
They absolutely are. And to understand why that matters, you really have to understand the fundamental problem with plain water. You mentioned surface tension a minute ago. Think of a drop of water on a freshly waxed car hood.
Okay.
What does it do?
It stands up tall, it forms a really tight little bead. It doesn't want to flatten out at all. It just looks like a little glass marble.
Right. It actively pulls itself together. That's cohesion. Water molecules love sticking to other water molecules way more than they like sticking to the wax on your car.
Got it.
That skin holding the bead together is the surface tension. Now imagine that car hood is actually a piece of burning wood.
Or a bale of cotton.
Or a massive pile of rubber tires. If the water beads up, it has minimal contact area with the fuel. It doesn't soak in. It just sits right there on top.
Or worse, gravity takes over.
Exactly.
It rolls off the side, hits the floor, and you've wasted the water while the fire is still burning inside the material.
In a fire scenario, especially a deep-seated one, you really don't want beads. You want a film. You want a flat sheet of water. A wetting agent breaks that tension. It relaxes the water.
It forces it to flatten out.
Yes, it allows it to cover more surface area And most importantly, soak deep down into the microscopic pores of the fuel. It literally turns water from a barrier into a penetrator.
So the mission of this deep dive is to decode exactly how they prove that works. Because under NFPA 18, you can't just claim your stuff works.
Oh, definitely not.
You can't just slap a sticker on a jug that says, make water wetter and sell it to a fire department. You have to survive a serious gauntlet of tests.
It is absolutely gauntlet. And it starts with the raw physics and the chemistry.
Let's get right into Section 1, the physics of wetter water. The document makes a very big distinction right off the bat between the concentrate and the solution.
This is a vital distinction for anyone handling these materials and really for our understanding of the testing procedures we'll talk about. The wetting agent, or the concentrate, is the raw chemical in the shipping container.
The stuff you buy.
Right. It's thick. It's incredibly potent. The wetting agent solution is what happens after you actually mix it with water.
So to use a really simple analogy, the solution is the soda in your glass, whereas the concentrate is that thick syrup in the bag hidden in the back of the fast food fountain.
That's a perfect way to visualize it.
And the standard has very specific metrics for that solution. We talked about surface tension being the enemy here. NFPA 18 actually gives us a magic number, a literal pass or fail line for the laws of physics.
It does. This is found in Chapter 5, specifically Section 5.3.1. To pass the test and be officially listed as a wetting agent, the solution, when mixed at the manufacturer's recommended concentration, must reduce the surface tension to less than 33 dynes per centimeter.
33 dynes. Okay, let's unpack that for a second. First, what exactly is a dyne? And second, what is the surface tension of normal, everyday water? Just so we have a baseline to compare it to.
Sure. A dyne is a unit of force in physics. Specifically, it's the force required to accelerate a mass of 1 gram at a rate of 1 centimeter per second squared.
So a very tiny unit.
Very tiny, yeah. It's often used in measuring surface tension across liquids. Normal water, just out of the tap at room temperature, has a surface tension of about 72 dynes per centimeter.
Wow. Okay, so we are talking about cutting it by more than half.
Exactly. You're taking that 72 dynes of skin strength, which by the way is remarkably high for any liquid, and slashing it down to below 33.
And why is that specific drop so important?
That is the threshold where water stops behaving like water and starts behaving almost like a penetrating oil. It creates a massive sudden increase in the ability to soak into Class A combustibles.
Why 33, though? Why not 35? Or just round it to 30?
33 is generally accepted in the scientific community as the tipping point, where you get that super penetration effect in common porous materials, things like wood char and raw cotton. If you were at 60 dynes, you are still beating up way too much. At 33, you are flat.
So if I have a liquid that I've invented in my garage, and I claim it's a revolutionary wetting agent, but it only gets the tension down to 40 dynes...
Then according to NFPA 18, it fails. Period.
No exception.
None. It is not a compliant wetting agent. It might be slightly wetter than normal water, but it absolutely does not meet the standard for superwater. That 33 number is the hard line in the sand.
What about the chemistry of the concentrate itself? Because I noticed looking through the source that there are strict rules about pH balance. Which makes sense considering you're pouring the stuff into incredibly expensive metal tanks.
Yes. Chemical stability is key. You really don't want to put something in a fire truck that is going to turn into acid or bleach over time as it sits in the bay. The standard requires the pH of the concentrate to be firmly between 6.0 and 9.0.
That seems like a pretty safe, middle-of-the-road range. Basically neutral to just slightly basic.
It is. 7.0 is perfectly neutral, like pure distilled water. 6.0 is slightly acidic, think like milk or maybe human urine. 9.0 is slightly basic, closer to baking soda.
So why is staying in that window so critical?
The annex of the standard explains exactly why this matters. If the pH drops significantly below 7 into the highly acidic range, you start eating away at the steel components of the pump. If it goes above 12, becoming highly caustic, you start rapidly dissolving the aluminum parts.
And since modern fire trucks and industrial suppression systems are basically entirely made of steel, brass, and aluminum...
Going outside that range is a complete recipe for disaster.
Right. You are trying to solve a fire problem, not create a massive maintenance nightmare where your tank rusts completely through from the inside out. A new fire truck costs hundreds of thousands, sometimes over $1 million.
You definitely don't want a $50 bucket of specialized soap to ruin it.
Speaking of problems, and specifically where to actually use this stuff, let's move into Section 2. Where can you actually use a wetting agent? Because my assumption, rather naively before reading this, was just it's wetter water. Just use it everywhere. Why wouldn't you want wetter water on every fire?
That's a logical thought.
Right. But NFPA 18 has some giant red flashing warning lights on that idea.
It definitely does. You absolutely cannot just spray this indiscriminately. The standard breaks fires down by class, and wetting agents are really only designed for 2 specific classes, with huge caveats on the others.
Let's talk about the green light scenarios first. Where does this stuff really shine?
First and foremost, Class A fires. This is your absolute bread and butter for wetting agents. Ordinary combustibles. Wood, cloth, paper, rubber, many everyday plastics.
This is where that penetration ability we talked about, that below 33 dynes physics trick, really pays off.
Immensely.
Give me a real-world example for the listeners of where this clearly beats normal water.
Imagine a massive mulch fire at a landscaping facility,
Yeah.
or a peat bog fire out in the wildlands, or even a deep landfill fire. These are what we call deep-seated fires. The actual fire isn't just on the surface where you can see it. It's burrowed down 3, 4, maybe 5 feet into the pile.
Okay, so if you spray normal water on that.
It hits the top layer, it cools that top inch, creates a damp crust, and then just beads up. It doesn't travel downward. The fire burns happily right underneath that mud crust you just made.
It tunnels.
It tunnels, exactly. Wetting agents, because they have that incredibly low surface tension, will actually soak into the mulch. They naturally follow the path of the fuel. Gravity pulls them right down through the microscopic gaps, and they get straight to the deep-seated heat source.
So for a haystack fire or a hoarder house mattress fire, this is the gold standard.
Without a doubt.
What about Class B fires?
Class B covers flammable liquids, oils, tars, alcohols, basic solvents. But, and this is a massive, critical, but NFPA 18, Section 4.2.3.1, puts a very strict limitation right here.
I remember this.
You can only use wetting agents on Class B fuels that are not soluble in water.
Okay, we need to break that down for everyone. Soluble in water. That means liquids that physically mix with water, right?
Correct. Think about rubbing alcohol or acetone. If you pour water into a glass of vodka, it mixes perfectly and instantly. That's soluble. If you pour water into a hot pan of motor oil, the oil floats on top. They separate. That's non-soluble.
So the hard rule is if the fuel mixes with water, you cannot use a wetting agent.
Generally, no. Not unless it is very specifically listed and tested for that exact chemical.
Why is that?
Here's why. If you have a large pool of burning alcohol and you dump a wetting agent solution directly into it because they readily mix, you are essentially just diluting the fuel.
You aren't really fighting it.
No, you aren't forming any sort of barrier on top to stop the flammable vapors from escaping. You were just making a much larger, slightly less flammable puddle. You might actually be spreading the fire dynamically by increasing the physical volume of the burning liquid.
Wow. Okay, whereas with oil...
With oil or something like heptane, the water usually sinks to the bottom. But the wetting agent, if it's designed correctly, can help create a temporary emulsion right at the interface.
An emulsion?
Yeah, or at least cool the fuel more efficiently by massively increasing the surface area contact right at that liquid interface.
Yeah.
But it's vital to note it works very differently than traditional firefighting foam, which just sits on top like a thick blanket.
We are going to get to the actual testing on Class B later, because that is a whole ordeal in itself. But I want to talk about the runaway scenarios now. The places where using a wetting agent is explicitly, under no circumstances, allowed.
Yes, the prohibited uses.
The first one that jumped right out at me in the source was Class D fires.
Class D covers combustible metals, things like magnesium, titanium, zirconium, sodium. These are terrifying fires for responders. They burn incredibly hot. We're talking thousands of degrees.
And the rule in Section 4.2.5 is just completely uncompromising.
Very clear. Do not use wetting agents unless specifically listed for this exact purpose, which is incredibly rare.
Why is it so dangerous? Is it just because the water evaporates way too fast to do anything?
It's so much worse than that. It goes right back to the chemistry. Many of these exotic metals are highly water reactive. If you throw water wetter or otherwise onto a burning sodium fire, you are going to get a violent explosion.
Because it releases gas.
Yes, you are instantly releasing pure hydrogen gas.
Hydrogen gas, which is obviously highly explosive.
Extremely. And here is where the wetting part of the agent actually makes it so much worse.
How so?
Because a wetting agent deliberately reduces surface tension. It spreads over the burning metal way faster and way more completely than plain water would.
Oh, wow.
Yeah, so you are artificially maximizing the physical contact area between the water and the reactive metal in milliseconds.
So you essentially take a fire, turn it into a bomb, and you make the fuse way shorter.
Essentially, yes.
Yeah.
You are adding highly volatile fuel to the fire in the most violent, rapid way physically possible.
Okay, duly noted. Absolutely no wet water on burning magnesium.
All right.
What about Class C electrical fires?
This is a really interesting nuance in the NFPA standard.
Right.
Obviously, plain water and electricity don't mix because of the shock hazard.
Right.
If you spray a hose on a live high-voltage transformer, the electricity travels right up the water stream to the brass nozzle and violently shocks the firefighter holding it. That's basic firefighting 101.
Sure.
But the annex in NFPA 18 points out a very specific secondary danger with wetting agents.
What's that?
It's the residue. If you spray plain distilled water on a complex electrical panel, assuming the power is completely cut first, the water eventually just evaporates. It leaves very little, if anything, behind.
Makes sense.
But wetting agents are complex chemicals. They leave behind a noticeable residue. And the annex explicitly warns that this chemical residue can remain highly conductive.
Wait, so even after the equipment dries out completely?
Yes, you spray the panel, the fire goes out, the water evaporates into the air, circuit board looks bone dry, you flip the main breaker back on,
And boom.
boom, the invisible residue creates an immediate short circuit or a massive arcing path.
That is fascinating. So the equipment is basically ruined or at least permanently hazardous, even after it looks completely fine to the naked eye.
Correct. The standard clearly states it constitutes a severe hazard when the equipment is put back in operation. So you really have to be careful about collateral damage. You might save the physical room from burning down, but you permanently destroy the million-dollar farm inside it.
And the third no-go zone was commercial cooking, specifically the deep fat fryer.
This is a classic, terrifying kitchen nightmare. Section 4.2.3.2 is totally explicit here. You cannot use wetting agents on cooking, meaning combustible vegetable or animal oils and fats, unless it is specially listed for it.
Is that just because of the splash factor, hitting hot oil with water?
It's partly that, but it's really the chemistry of the specific fire suppression. Grease fires in commercial kitchens are usually fought with Class K wet chemical systems. Those specific chemicals are highly alkaline, and they chemically react with the hot grease to cause a reaction called saponification.
Saponification, that's the chemical process of actually making soap, right?
Exactly right. It chemically turns the top layer of the burning grease into a thick, foamy layer of non-flammable soap. It totally smothers the fire and seals in the vapors.
And wetting agents don't do that.
No, they don't necessarily do that at all. If you dump a standard wetting agent into an industrial deep fryer, you likely won't get that nice soap layer. Instead, because the water penetrates so incredibly well, it sinks instantly through the oil to the very bottom of the 400-degree fryer.
And since water boils at 212 degrees Fahrenheit?
It flashes into steam instantly at the bottom. And remember, water expands roughly 1,700 times its volume when it converts to steam.
That's a massive expansion.
So it effectively explodes upward from the bottom of the fryer, violently throwing burning, boiling oil all over the kitchen, the ceiling, and unfortunately, the firefighter.
So the takeaway is stick to the Class A stuff and the non-soluble Class B fuels unless you really truly know what you are doing with specialized equipment.
That is absolutely the safe bet.
Huh.
Read the label, know your exact fuel.
There is one more major warning in this section that honestly sounded like something straight out of Ghostbusters. It basically says, don't cross the streams.
The mixing warning. Section 4.3.1. Never mix different wetting agent concentrates together in the same holding tank.
What actually happens? Do they explode?
Usually it's far more gross than explosive. The annex describes the resulting reaction as coagulation. You could literally turn your expensive liquid concentrate into a thick jelly or a hard sludge.
Just massive amounts of Jell-O inside the fire truck's plumbing.
Imagine trying to pump thick Jell-O through a high-pressure mechanical fire pump and out through a narrow nozzle. It completely clogs the equipment, it won't proportion correctly into the water stream, and you instantly lose all of your firefighting ability.
Plus the cleanup.
The cleanup is a nightmare, and it can also cause immediate aggressive corrosion inside the pipes.
Why does that happen just from mixing two brands?
Because different manufacturers use completely different chemical bases. Some might be anionic, carrying a negative charge, while some might be cationic, carrying a positive charge. If you mix those positive and negative charges together in a tank, they snap together chemically and form dense solids.
So if a city fire department decides to change vendors, like switching from brand X to brand Y to save money, They have to be incredibly careful.
They have to heavily flush that entire system. You cannot just top off the tank with the new stuff. You have to drain it completely, flush it with pure water multiple times, and then fill it. Otherwise, you might literally brick your $500,000 fire truck.
It's amazing how delicate the chemistry actually is. You just think, oh, it's just industrial soap. Surely they all mix fine.
Yeah.
But it's really a carefully balanced, highly engineered chemical weapon.
It truly is.
Hmm.
And because it's a chemical weapon, we are spraying openly into the natural environment. We really have to talk about Section 3, the toxicity trials.
Right. This was the part of the source document where I suddenly realized just how much raw biology is involved in modern fire safety. Because when firefighters spray this stuff on a burning building or a massive wildland fire, it doesn't just magically disappear.
Not at all.
It goes right into the ground. It goes down into the city's storm drains, and it eventually ends up out in the rivers and lakes.
That's right. The toxic runoff is a major, major environmental concern. You obviously don't want to save the forest from burning, only to completely poison the river running right through it. So the NFPA mandates rigorous environmental testing, directly referencing EPA, OPPTS, and ASTM scientific standards. They test on mammals, and they test on fish.
Let's talk about the fish, the rainbow trout test. This seemed incredibly, almost weirdly specific in the document.
It is actually the gold standard in the industry for aquatic toxicity. The specific test subject mandated is Oncorhynchus mykiss, the standard rainbow trout.
Why the trout, specifically? Why not test on cheap goldfish or maybe bass?
Because trout are incredibly sensitive to their environment. They are very high-maintenance fish biologically. They need very cold, perfectly clean, highly oxygenated water to survive. They act as what we call a sentinel species.
Like a canary in a coal mine.
Exactly. They're a great early indicator for the overall health of a freshwater ecosystem. If the trout are dying, your entire ecosystem is in deep trouble. If the trout are fine, the hardier fish like the bass and catfish are almost certainly fine too.
So how does this test actually work? Do they just drop some of the soap in a fish tank and wait?
It's incredibly controlled.
Yeah.
They take a specific number of these trout and carefully expose them to the diluted wetting agent solution for 96 straight hours.
That's 4 full days.
4 full days of exposure. And they have to control the environment perfectly so there are no other variables. They use a specific soft water defined by ASTM standards because water hardness can actually alter the toxicity of the chemical. And the temperature of the water has to be maintained at exactly 12 degrees Celsius, plus or minus just 1 single degree.
12 degrees Celsius, that's pretty chilly. That's like 54 degrees Fahrenheit.
Right, because that's the preferred optimal temperature for a rainbow trout. They absolutely want to ensure that if these fish die during the test, it's strictly because of the chemical agent, not because the water was too hot or the oxygen levels dropped too low. It completely isolates the chemical variable.
And what is the official passing grade for this?
They measure something specific called the LC50. That stands for the lethal concentration for 50% of the population.
Okay.
Basically, they figure out at what exact concentration of the chemical does exactly half the tank of fish die.
A bit morbid, but highly scientific.
Very. To pass NFPA 18 and be listed, the LC50 of the agent must be greater than 10 milligrams per liter.
Okay, let's make sure we totally understand the math here for you listening. If the LC50 number is higher, that actually means the chemical is safer, right?
Correct. That's often very counterintuitive for people reading these standards.
Right. Usually high numbers are bad.
Yeah, but think of it this way. If the LC50 is, say, 100 milligrams per liter, it means you can pump a whole lot of the stuff into the water before the fish actually start dying.
Got it.
But if the LC50 is just 1 milligram per liter, it means a tiny microscopic drop kills them all. So the NFPA sets the absolute safety floor at 10. If it takes less than 10 milligrams to kill half the fish in that tank, that means the stuff is just way too toxic, and it outright fails. It cannot be listed for use.
But they don't just care about the fish out in the woods. They care about the firefighters handling it in the station, too.
Oh, absolutely. That brings us to mammalian toxicity. This entire section exists to protect the people physically handling the heavy concentrate. They test for acute oral toxicity, meaning what happens if someone accidentally swallows it, and acute dermal toxicity, meaning what happens if it spills all over your bare skin.
And there was a section on eye irritation, too.
Yes, primary eye irritation is a big one. For the oral toxicity test, the safe baseline is an LD50 lethal dose instead of lethal concentration of greater than 500 milligrams per kilogram of body weight.
Break that metric down for us a bit.
If the LD50 is greater than 500, it's considered relatively safe for general handling. If it falls between 50 and 500, The standard says you technically can still use it, but you need very strict hazard labeling, specialized protective gear, and heavily regulated safe handling procedures.
And what if it's below 50?
If it's below 50, it is officially marked as not acceptable. You simply cannot list a product that toxic under NFPA 18. It's just way too dangerous to have sitting on a chaotic fire scene where massive spills happen constantly.
That makes total sense. There was also this 28-day challenge regarding biodegradability that I found really interesting.
Yes, the environmental persistence test. We absolutely don't want these suppression chemicals lingering in the topsoil for decades, like the PFAS foam issues or other forever chemicals we hear about in the news. The standard demands the agent be readily biodegradable.
What is the exact metric they use to define that?
They measure exactly how much of the chemical complex naturally breaks down over a set time. Specifically, they measure how much oxygen the natural bacteria in the sample consume while they are eating the chemical. To earn the readily biodegradable tag, 60% of the chemical mass must completely break down within 28 days.
That actually seems pretty fast. Just 4 weeks to get rid of the vast majority of the synthetic chemical.
It is fast. It ensures that the environmental footprint of the fire response is strictly temporary. The test can technically be extended out to 42 days if the breakdown process is still visibly happening and hasn't plateaued yet. But the ultimate goal is rapid, natural decomposition. You want it to aggressively do its job on the fire and then quickly disappear into nature.
Okay, so we know it works purely on physics. By hitting that 33 dynes mark, we know exactly where to use it on Class A and B fires, and we know it won't instantly kill all the trout. But now we really have to talk about what it does to the incredibly expensive fire equipment. Section 4, the corrosion torture chamber.
This is hands down one of the most grueling, punishing parts of the entire certification process. As we established, wetting agents are chemically aggressive by nature.
Right.
They are specifically engineered to clean heavy grease and aggressively penetrate microscopic pores. Well, unfortunately, metal has microscopic pores. And if you chemically strip away the natural protective oxidation oils on a bare piece of steel, you are leaving the door wide open for rust.
The testing method outlined here was just fascinating. They use these tiny little metal strips called coupons.
Right. A coupon in this context is just a standardized, perfectly machined sample of material. For this specific test, they are exactly 25 millimeters by 102.6 millimeters by 3.2 millimeters thick.
That is absurdly specific, 0.6 millimeter.
Science requires absolute consistency. If the metal volume changes, the corrosion rates change. They test 4 very specific metals that you find in emergency equipment. 4130 mild steel, 2024 T3 aluminum, UNS C27000 yellow brass, and AZ31B magnesium.
I actually recognize that 2024 aluminum. That's aircraft-grade aluminum.
Exactly. It's a high-strength, copper-rich aluminum alloy widely used in modern aerospace. The 4130 steel is extremely common in truck tubing and chassis frames. The yellow brass is what practically all the heavy valves and nozzles are made of.
So if the wetting agent eats through any of these, it's going to systematically destroy your entire fleet of vehicles?
Precisely.
So walk us through this torture test. How do they actually do it?
They take these pristine metal coupons, carefully weigh them, and then suspend them inside a glass jar using a braided Dacron fishing line.
Okay, stop right there. Why a fishing line? Why not just hang it with a simple copper wire or a paper clip?
Because of galvanic corrosion.
Galvanic corrosion.
Yes. If you used a conductive copper wire to hang a mild steel coupon inside a chemical bath, you'd effectively create a crude battery. The microscopic electrons would actually flow between the two different metals, and the corrosion on the steel would accelerate artificially.
Oh, wow.
Yeah, so the test would be totally invalid. Dacron fishing line is completely non-conductive and chemically non-reactive. It perfectly isolates the variable to just the metal and the liquid.
Incredible detail. So they hang them in the jar. For how long?
90 continuous days, 3 full months, and they run 2 separate modes for the test. Total immersion, where the coupon is completely drowned at the bottom of the wetting agent, and partial immersion, where it's exactly half in the liquid and half out in the air.
I assume that half in, half out methods to test for waterline corrosion.
Exactly right. The physical interface between the liquid chemical and the open air is very often where corrosion is the most hyper-aggressive, because right there you have plenty of atmospheric oxygen readily available to heavily fuel the chemical oxidation process. If you have a fire truck tank that is sitting half full in the bay, That exact water line is where the deep rust starts eating the wall.
So 90 days later, they pull these little strips out of the jars. They must be completely covered in horrible gunk.
They are totally unrecognizable.
Right.
And this is where the laboratory procedure gets very, very specific. You cannot just weigh them immediately because the heavy rust adds mass or the congealed chemical gunk adds mass. You actually have to strip them down perfectly to the bare, uncorroded metal to see exactly how much actual base metal was eaten away by the chemical.
And I read they have highly specific acid recipes for cleaning them.
They absolutely do. For the brass coupons, they scrub it down with a 15 to 20% hydrochloric acid solution. For the aluminum, it's 70% nitric acid.
And for the steel?
Steel gets a wild cocktail. It's a precise mix of tin chloride and antimony chloride dissolved in acid.
And the high-tech tool of choice for this intense scrubbing process.
A standard toothbrush.
I love that so much. High-tech, incredibly dangerous acid cocktails applied carefully with a drugstore toothbrush.
Or a standard non-metallic scouring pad. But yes, the goal is to gently remove all the oxidized scale without accidentally scrubbing away any of the remaining healthy metal underneath. Once it's perfectly clean and dried, they weigh it on a microscale. The microscopic difference in weight tells them exactly how much solid metal was lost to the chemical.
And they convert that weight loss into a standardized number, MPY, mils per year.
Right. A mil is 1/1000th of an inch. They project the data out. If we left this chemical sitting in the tank for 1 full calendar year, exactly how many thousandths of an inch of the metal wall thickness would we lose to rust?
What's the acceptable limit?
Generally, for ground equipment like the steel and brass on a fire truck, the hard limit is 5.0 MPY. If you lose 5 mils a year, that's considered structurally acceptable for a heavy ground vehicle. But there is a much, much stricter limit for the aluminum used in aircraft like fixed-wing air tankers or fire helicopters.
Obviously, because you really, really don't want a corrosion hole forming in an airplane tank while you're flying over a forest fire.
Correct. And the overall structural integrity margins are just so much higher stakes in aviation. For aircraft aluminum, the limit is strictly 2.0 MPY.
Wow.
It has to be more than twice as gentle as the stuff used on the ground.
That makes perfect sense. Okay, let's move along to section 5, stability and logistics. This is basically the, will it actually work after sitting on a shelf in a hot fire station for 6 months section.
This is critical for real-world application. Fire chemicals aren't always used immediately after they're bought. They sit in storage. The standard requires a mandatory 30-day shelf life test where they actively check for physical separation.
Like when a bottle of Italian salad dressing separates in the fridge.
Exactly like that. Chemical stratification. If the heavy chemical compounds sink to the bottom of the jug and the lighter water floats to the top, and a firefighter tries to pump it into a hose, they are getting the completely wrong mix ratio. The product automatically fails if it separates into distinct layers or precipitates solid junk to the bottom of the container.
They also rigorously test temperature extremes, right? Freezing and baking.
Yes. They freeze the concentrate solid at -18°C, which is 0 Fahrenheit, and they bake it at 49°C, or 120 Fahrenheit. After they carefully thaw it out or cool it back down to room temp, they have to run that surface tension test all over again.
To make sure it didn't degrade.
Right. And it absolutely cannot vary by more than 5 dynes from the original baseline spec.
So it literally has to survive a brutal winter in Minnesota and a baking summer in Arizona and still work perfectly within a tiny margin of error.
Correct. It has to be incredibly robust for logistics.
I also really loved the miscibility test, the stirrer test.
Yes. This measures how easily the thick, syrupy concentrate actually mixes with flowing water. You really don't want to have to physically shake the fire truck to get the soap to mix. It should blend instantly as it flows through the pipes.
The diagram in the source for this specific test is just hilarious. It's extremely precise for such a simple concept.
It is. It mandates the exact dimensions and blade angles of the mechanical stirrer shaft. They drop the thick concentrate directly into the water and spin the stirrer at exactly 60 revolutions per minute.
And they literally count the revolutions.
They manually count the turns. The standard explicitly states it must become a perfectly uniform mixture within 100 revolutions.
That is strict. 100 turns at 60 RPM. That's less than 2 minutes of mixing time.
It's roughly a minute and a half. Because in a live fire scenario, you just don't have time to sit and wait. The mechanical induction system on the truck works incredibly fast. If the chemical doesn't mix instantly as it hits the fast-moving water stream, you're just spraying plain water at the fire. It needs to blend on contact.
There is one last thing on logistics regarding leakage. The annex had a fascinating warning about using this stuff in older fire trucks.
Yes. This is a very practical, real-world warning for fire chiefs. Because wetting agents artificially reduce surface tension, they are essentially thinner than normal water in a functional mechanical sense. They can easily slip through microscopic gaps in metal that normal water simply can't penetrate.
So the truck might be completely watertight, but not wet watertight.
Exactly. If you have an older truck with slightly worn packing glands or older rubber seals that are holding back normal water just fine, the very second you introduce a wetting agent into that plumbing, they might start dripping uncontrollably.
That's wild.
It's a very common maintenance issue when departments excitedly switch to these agents without fully upgrading their internal seals. The extreme wetness actually works against you there.
Okay, we have thoroughly covered the complex chemistry, the biological toxicity, the metal corrosion, and the shelf life logistics. But now, we finally get to the main event. Does it actually put out a fire? Section 6. Trial by fire.
This is where the rubber meets the road, or I suppose where the wet water meets the burning wood.
The Class A extinguishment tests. There are 3 distinct tests. The first one is the wood crib.
This is a very standard test across the entire fire suppression industry. It's a standardized, precisely built stack of kiln-dried wood, built to a very specific geometric shape to ensure perfect airflow and a known fuel load. It's officially rated as a 3A fire. They use a standard 2.5-gallon extinguisher filled with the properly mixed wetting agent solution.
And the requirement to pass is pretty simple.
Very simple. Put the fire out entirely. It just proves basic, baseline efficacy.
But the second test. The second test is the one that really captures the imagination, the deep-seated fire test, or as I started calling it in my notes, the cotton basket.
This is the ultimate undeniable test of wetness. This perfectly simulates a fire burning deep inside a thick mattress or a dense bale of raw cotton where you can't even see the open flame, but the massive heat is buried deep inside. This is the exact scenario where plain water completely fails because of that surface tension skin.
Describe the testing rig for us, because it's pretty wild.
They use a specially perforated steel basket, about 4.5 inches wide, and they take exactly 100 grams of raw gin cotton.
Why cotton specifically?
Because raw gin cotton is extremely fluffy and porous, but it's also naturally waxy and highly hydrophobic. It really doesn't like to get wet. It's notoriously hard to penetrate with a hose. They stuff exactly half of that cotton tightly into the bottom of the steel basket. Then they introduce the heat source, a solid steel rod, 35 millimeters thick.
And how hot is this metal rod?
They heat it in a furnace to exactly 593 degrees Celsius. That's 1,100 degrees Fahrenheit. It is literally glowing red hot.
So they just drop this glowing metal slug directly onto the raw cotton.
Yes, it immediately starts heavily scorching and burning the cotton. Then they immediately stuff the remaining half of the cotton tightly on top of it. So the glowing heat source is now completely buried in the dead center of a dense fuel ball.
And then they pour the liquid on.
They carefully pour exactly 250 milliliters of the wetting agent solution directly onto the top of the cotton. Now remember what we said about surface tension. If this were normal, everyday water, it might just run down the sides of the steel basket, following the path of least resistance. It would never penetrate the dense, waxy cotton to hit that rod.
And if it doesn't physically hit the rod, the cotton just keeps burning from the inside out.
Exactly. The ultimate goal is for the liquid to rapidly soak straight down through the cotton, make physical contact with that 1,100-degree rod, and aggressively cool it down below the ignition point.
How do they quantitatively measure success here?
They measure the physical runoff. They place a catch pan underneath the suspended basket. If the liquid just runs quickly through the edges of the basket without soaking into the cotton, it collects down in the pan. Less liquid runoff means much better absorption into the fuel. And of course, the primary requirement, the fire has to completely go out. If the cotton is still noticeably smoldering after a set time, or if it reignites, the chemical fails.
That is a brutal, demanding test. It's purely checking that specific property of deep penetration.
It undeniably proves that the 33 dynes surface tension measurement we talked about actually translates directly to real-world firefighting performance. It connects the sterile lab number to the chaotic fireground reality.
There's a third Class A test too, wood fiberboard penetration.
This is conceptually similar to the cotton basket, but it focuses heavily on common building materials. They take 12 by 12-inch square panels of standard fiber insulation board, which is very dry, porous stuff. They aggressively burn them with an alcohol flame for exactly 1 minute and 45 seconds.
Just to get them really good and hot.
Right, establish a deep char layer. Then they spray the burning board with the wetting agent. Once again, they weigh the board before the test and after the test, and they carefully measure the liquid runoff. They want to see verifiable proof that the charred board has deeply absorbed the liquid, actively gaining weight from the trapped water, and that the water hasn't just bounced off the carbonized surface.
So the ideal result is less runoff, more retained absorption, fire goes out.
That is the required trifecta to pass.
Finally, we have Section 7, the Class B fire test. We established much earlier that wetting agents are only ever approved for non-soluble liquid fuels. So how do they rigorously test that?
They use a chemical called heptane. Heptane is a very standard, highly volatile hydrocarbon fuel used in lab testing. It naturally floats on water. It absolutely does not mix. It produces a very violent, incredibly smoky fire.
What's the exact physical setup?
They build a massive 50-square-foot steel pan. They fill the base with a layer of water and then carefully float a 2-inch deep layer of pure heptane right on top.
A 2-inch layer of fuel over 50 square feet. That is a lot of fuel. 50 square feet is basically the size of a small room.
It is a highly significant fire. They ignite it and let it free burn, completely untouched, for 60 full seconds. If you've ever seen a 50-square-foot heptane fire in person, it is absolutely roaring after a full minute. The radiant heat output is massive.
And then the attack finally begins.
They apply the wetting solution at a strictly fixed rate of exactly 10 gallons per minute. They can use either a fixed, mounted nozzle or a moving nozzle, which simulates a human firefighter sweeping a hand line.
And the clock is officially ticking.
The hard requirement is to fully extinguish that roaring fire within 5 minutes.
5 minutes actually seems like a pretty long time compared to traditional foam tests I read about, where they often knock the fire down in like 60 seconds flat.
It is longer. But remember, specialized foams are engineered to violently expand and instantly blanket and smother a fire. Wetting agents work very differently on liquid fires. They rely on rapidly cooling the fuel surface and slightly emulsifying that top layer. But here's the major catch. Unlike those foam standards, like NFPA 11, there is absolutely no burn-back requirement here.
What exactly is a burn-back test?
Burn-back tests actively measure if the liquid fuel fire can easily reignite after you intentionally stop spraying and introduce a new ignition source. Heavy foam forms a thick, durable physical blanket that prevents that reignition for a very long time.
Oh, I see.
Wetting agents just don't form that thick, lasting blanket. Once the fire is totally out, it's out, but the chemical vapor seal left behind isn't nearly as robust as foam. That's why this specific standard doesn't require a burn-back test. It just strictly requires initial extinguishment.
But they do heavily require consistency in the testing.
Yes, they do. To officially pass Section 7, you have to successfully put out that massive fire 2 times in a row. 2 completely consecutive tests. If you pass the first one perfectly, but fail the second attempt, you have to start the entire process over. You need to definitively prove the first success wasn't just a random fluke of the wind.
That makes total sense. Reliability is absolutely everything. When a firefighter pulls that lever on the pump panel, it has to work perfectly every single time, without question.
Absolutely. Lives depend on it working exactly as advertised.
So bringing this entire massive document together for you listeners, we started today with just a simple bucket of water. We asked if it was really wet enough.
And we learned that to make it functionally wet enough for modern high-stakes industrial fires, we really have to deeply engineer it. We have to fundamentally, chemically alter its physical properties.
We have looked at the incredible life cycle journey of a wetting agent. It starts out as a carefully pH-balanced concentrate between 6 and 9 that absolutely won't separate into layers while sitting on the shelf.
It has to survive freezing completely solid in Minnesota and baking in Arizona. It gets rapidly mixed into the water stream to pass that strict 100 revolutions stirrer test.
It has to be proven non-toxic enough to keep the highly sensitive rainbow trout alive with an LC50 greater than 10 milligrams per liter and readily biodegradable enough to mostly vanish into the environment in just a month.
It has to be chemically gentle enough not to rapidly eat through the vital aluminum tank of an aerial firefighting helicopter, staying under that strict 2.0 MPY limit.
And finally, after all of that, it has to be able to physically penetrate a densely packed, burning basket of raw cotton to instantly cool an 1100-degree solid steel rod.
It really heavily highlights the incredible unseen value of proper standardization in our modern world. Without a rigorous document like NFPA 18 holding the line, literally anyone could bottle and sell magic fire soap that covertly ruts out your million-dollar tanks, electrocutes your crews, and kills all the fish in the local river system.
That is exactly why these dry, incredibly dense standards exist. It fully protects the firefighters from catastrophic equipment failure, it protects the fragile environment from unchecked chemical toxicity, and it protects the property owners by guaranteeing the fire actually goes out when it's supposed to. It completely prevents snake oil salesmen from entering the safety market.
I couldn't agree more.
So, here is my final, slightly provocative thought for you listeners to mull over today as we wrap up. We usually just think of wetness as a simple, everyday physical sensation. You touch something damp and it just feels wet.
But as we've seen in the physics section today, wetness really isn't a feeling at all. It's a quantifiable force.
Exactly. It's a highly measurable, manipulable force. 33 dynes per centimeter. That exact mathematical number is the invisible line between total success and catastrophic failure. And in the high-stakes world of fire safety, overcoming the rigid physics of water's own cohesive skin is literally the defining difference between saving a building and just standing there watching it burn to the ground. It really makes you wonder what other simple, everyday physical forces we take for granted that are secretly dictating the limits of our technology.
That is a genuinely powerful thing to remember the very next time you see a heavy fire truck roll past. They aren't just carrying hundreds of gallons of water. They are carrying highly engineered, weaponized chemistry.
Thanks for joining us on this incredibly detailed deep dive into NFPA 18. We will see you on the next one.
Stay safe out there.